the last class we saw the generalized correlation which is applicable to a wide variety of maybe gases. We said that it can be written of the form Z equals Z0, Z superscript 0 plus omega, which is the eccentric factor, times Z superscript 1. We said this, we said that we could write this because the values of Z0 and Z1 are available in tables along with the values of the eccentric factor omega for different pure substances. And even if the tables are not available, we said that there are analytical expressions which work reasonably well. What we will start doing in today's class is to get a little more comfortable with the generalized correlations, generalized relationships. To do that, we will work out an example or an exercise. So, this is example 3.3. Find the volume needed in example 3.1 for isopropanol using the generalized correlations and compare it with the ideal gas volume as well as the one obtained with virial coefficients. This is going to be the question. As I said, isopropanol is going to be one of our favorite compounds. It has a lot of biological applications. What I do is let you think about how to go about doing it, get your bearings straight. How do you, what we need is the volume, the same as example 3.1 for isopropanol under the same conditions, but this time we are asked to use the generalized correlations and of course compare it with the ideal gas volume as well as the one obtained with the virial coefficients. These two we already have from the previous examples. So, can you take a few minutes, maybe 5 minutes, to see how you would go about doing it, and then I will present a part of the solution. Go ahead please. that you have familiarized yourself with what the generalized correlation is and where you could get the values for isopropanol of Z0, omega and Z1. Let us take a look at the part of the solution. To use the generalized compressibility factor correlation, we definitely need the values of the critical constants. You go back and see the relationships, you would know that you would need critical constants, and the critical constants, as we have already seen before, are available in appendix B of your text, and the compound that we are looking at, the pure substance that we are looking at, is isopropanol. I think it is listed under 2-propanol for in your appendix of Smith, Vannes and Abbott, and if you take a look at that, you may have already done that in the time that was given. You would find that the critical temperature is 508.3 Kelvin and critical pressure is 47.62 bar. You have already seen this in the earlier examples, you needed it in the earlier examples also. Therefore, the reduced temperature, this is essentially why we were looking at the critical constants, so that we could calculate the reduced temperatures, and therefore we could use the generalized correlations. The reduced temperature, you need the temperature in Kelvin, and therefore you add 273 to the temperature given in degrees C. This is the critical temperature 508.3, 200 was given in the earlier example 3.1, 200 plus 273 to get it in Kelvin and critical temperature 508.3. Therefore, the reduced temperature turns out to be 0.931, and similarly the reduced pressure, the 10 bar in 200 degrees C were the conditions, 10 by the critical pressure 47.62 bar turns out to be 0.21. Now, this is the generalized correlation, and the values of Z0, Z1 and omega need to be obtained from the tables in the appendix of your textbook. From the appendix E of your textbook, you would get Z0 for the particular PR and TR as 0.9115 and Z1 as minus 0.0326. Note that this is a function of PR and TR, and the strength of this particular formulation is that you could get Z0 and Z1 only as a function of PR and TR and use it for all pure substances, and the acentric factor which brings in the aspect of the pure substance here, as we saw in the development, this was needed from appendix B turns out to be 0.668 for isopropanol. Therefore, if you substitute into this expression Z0 0.9115 plus acentric factor 0.668 times Z1 0.0326, do the calculations, you will get 0.8897. Okay. I will give you another 10 minutes to do the calculations to get the volume as well as for the comparison. Please go ahead and do the calculations. You have enough basis, you know that Z equals PV by RT. So, please go ahead and do it. Let us continue. V, this is the calculation point ZRT by P, Z is PV by RT. So, transposition gives V equals ZRT by P, the molar volume. Z we have found as 0.8897, R of course is 8.31, T is 473, that is 200 degrees C is 473 Kelvin, and 10 bar is 10 power 6 Newton per meter squared, 10 into 10 power 5, and the if you do the calculations, it will turn out to be 3.497 into 10 power minus 3 meter cubed per mole. So, that is the molar volume. So, we have gotten whatever we need from the generalized correlations, and of course, go back to the earlier exercises and see how this volume compares with the volume obtained from the ideal gas relationship, which would result in a large difference, and also the one obtained with using the virial expansion. go ahead and do the comparison, and yeah, take 2 minutes to do it when you go back to your exercise and see how the values compare. Okay, you would have found out the improvement in the level of accuracy. Hopefully, if you compare it with the actual experimental value, you will know that, but at least you will see the difference between the value obtained with the generalized correlation and the ideal gas value. Definitely that would have been stark, and of course between the generalized correlations and the one obtained with the virial coefficients will give you some idea as to what differences to expect from these two approaches. Now let us do a further exercise. I am just going to present it and give you time to do it, so that will give you a means of first deciding how to do it, and that is the way to go about doing a problem. First decide how to do it and then substitute. So the extension is something like this. Suppose the appendix was not available to you, the textbook was not available to you, or in other words the tables of Z0 and Z1 were not available to you. If the values given in appendix E of Smith, Vannes and Abbott were not easily available, one can approximately calculate the generalized compressibility factors from the virial coefficients used in 322 and 323 using the value of TR. I have actually given you the way to go about this. What I would like you to do is do the calculations and see how much of a difference you get in the values. Take about 10 minutes to do this. Let us continue. Some of the solutions to earlier things are given here for comparison. You would have already seen that. Now, let us start looking at a totally different aspect, or the next aspect. Earlier it was all in terms of getting the equations of state or considering different equations of state to improve the generality of application. As you know, the equation of state is something that relates the P, V and T of a pure substance. Now, we are going to use that information P, V and T to estimate the other thermodynamic properties, and the way we are going to do that is use something called residual properties. If you use this formulation, it becomes possible to estimate the other thermodynamic properties. Remember that U, S, H, A and G, we could estimate the other properties using PVT. So, let us take a look at how to go about doing that. The motivation, as we all know by now, is that U, S, H, A and G are not easily measurable. They are of course estimated, they can be estimated by the more easily measurable P, V and T, and we are going to limit ourselves to gases to begin with. Pay a little bit of attention to this. For any thermodynamic property, okay, for the 5 that we are looking at now, you can write this for any thermodynamic property or even combinations of thermodynamic properties. The actual value minus the ideal value, or the difference between the actual value and the ideal value, is actually called the residual value. Now, to give you an example, if V is the actual molar volume of a substance and V ideal gas Vig is the ideal gas molar volume, then the residual molar volume represented as Vr is given as the difference between the actual value V and the ideal value Vig. Let us take this a little further. This is the basic definition of a residual property now given in terms of molar volumes, and since this is the molar volume, let us try to take this a little further. This is nothing but V minus V ideal gas is RT by P, and we know that PV by RT is Z, and therefore, we can write this as PV by RT, and therefore, if you take this out, you are going to get RT by P into Z minus 1. Rather, we are writing V in terms of Z, which is ZRT by P, and therefore, RT by P common out Z minus 1. We will call this equation 324. And since we can write this for any thermodynamic property, we could of course we will give you a formal expression for that. If M is any extensive thermodynamic property such as U, S, H, A, G or V, the residual property of that M is nothing but M minus M ideal gas. We will call that equation 325. Now, let us kind of deviate slightly. It is still very related, but this becomes essential to develop a means of relating the excess properties to PVT. Therefore, let us kind of deviate slightly and consider the quantity G by RT. The residuals of this could also be written, as you would see. We will start considering G by RT. Please work out the dimensions of G by RT. If you need, you can go back to your notes, find out what the dimensions of G are, R are, T are, and then work out the dimensions. Take about 3 minutes to do it and convince yourself that it is dimensionless. Okay, you should have gotten no dimensions for G by RT. If not, please check after the class. Now, let us consider the derivative, the total derivative of G by RT. You know that this is this is of a u by v form. R of course is a constant, but G and T are variables, and it is of the u by v form, and therefore the total derivative of G by RT is nothing but denominator function into derivative of the numerator function minus the numerator function into derivative of the denominator function divided by the denominator function squared. So, in other words, denominator function RT into derivative of the numerator function dg minus the numerator function g times the derivative of the denominator function RT divided by RT squared, which can of course be you take the common terms out, 1 by RT dg minus g by RT squared, one of the r's will get cancelled, g by RT squared times dt. Now, okay, we will call this equation 326. Now, let us express dg and g in terms of the expressions that we already know. In other words, we are going to use equation 2.8 for dg and 2.3 for g. You do not have to go back and check, you will these equations will come back to you when I substitute them. If you use these two equations in 326, dg by RT equals 1 by RT from here, dg is nothing but for a closed system minus STT plus VdP. So, that comes in here minus g by definition is H minus Ts. So, H minus Ts, that is equation 2.3 by RT squared dt, which can of course be simplified to V by RT dP minus H by RT squared dt. I am sure you can see this here. Equation 327. Now, this is the total differential. You know that total differential of an exact differential can be written as a partial differential times dou g by RT dou P dP minus or plus dou g by RT dou T dt. Therefore, this should be equal to, okay, let's take one step at a time. By considering g by RT as a function of P and T, we can write V by RT as dou g by RT dou P, this term at constant temperature here. We will call this equation 328, and H by RT equals minus T, because H by RT squared will turn out to be the partial derivative here with respect to temperature at constant pressure, and therefore, H by RT is minus T dou g by RT dou T at constant P. We will call this equation 329. By dividing equations 2.1 and 2.3 by RT, this will come back to you straight away. You don't need to go back. U was nothing but H minus PV, or H equals U plus PV. Therefore, U equals H minus PV, and you divide throughout by RT. U by RT is going to be H by RT minus PV by RT, equation 330, and S is S by R equals H by RT minus G by RT. Those are Ts, G equals H minus Ts, and from that we get S by R equals H by RT minus G by RT. What we will do now is we will stop here with this equation 331, because the further development we would like it to be a little more continuous, and we will continue with this in the next class.